Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
In 1845, there was this mathematician named Georg Cantor, and he basically stared right into the concept of infinity and tried to put it in a box.
Which is kind of a dangerous thing to do in math, honestly.
Right. I mean, it nearly destroyed his entire career.
Yeah.
Because he didn't just want to, acknowledge that infinity was this never-ending thing. He actually wanted to count it.
Yeah, he wanted to categorize it.
Exactly. To prove that some infinities are literally bigger than other infinities, which at the time was just such a radical idea that it completely split the academic world in half.
It really did. And, today we're going to explore the mathematical framework that made his whole obsession possible.
Which is set theory.
Yes,
Yeah.
set theory. And I know it might sound like this super esoteric, highly abstract branch of mathematics, but it's actually, well, it's the foundational operating system of human logic.
Wow. Okay. The operating system of logic.
Pretty much. It's how we categorize literally everything from, the physical objects sitting in your home, right down to the underlying architecture of search engines and databases you use every day.
And that is exactly our mission for this deep dive. We are taking this mathematical concept of sets out of the abstract void, and we're going to show you how it governs the way you process reality.
Absolutely.
And to do this, we're pulling our framework straight from section 1.1 of chapter 1 from contemporary mathematics.
Which is just the perfect starting point for understanding how we define boundaries in what is basically a totally chaotic universe. And just to keep things easy, from here on out, we'll just refer to it as section 1.1 or, simply the textbook.
Sounds good. Now, to tackle material that's this dense, we thought we'd establish a bit of a dynamic for you today. So I am going to step into the role of the inquisitive student.
Oh, boy.
Yeah, my job is to play the skeptic, right? I'm going to ask the questions that challenge these definitions and just demand to know how they actually apply to the real world.
Fair enough. And I'll gladly take the lecturer's podium to unpack the material, bridge those gaps between the abstract and the tangible, and, hopefully ensure we all walk away with a deeper understanding of this whole framework.
All right, lecturer, let's jump in.
Let's do it.
Before we can start, measuring the infinite, we have to establish what we're actually measuring, right? So when we use the word set in a mathematical context, what are the actual parameters? Because humans categorize things constantly, but, not all categories are created equal.
Right, they aren't. And the textbook grounds this with a super practical analogy. Think about a kitchen drawer organization system.
Okay, I have several of those, yeah.
Right, so if the physical drawer itself acts as the set, then the individual forks, spoons, and knives inside that drawer, those are the elements.
Okay.
So a set is simply a collection of objects, and the elements are the distinct objects that make up that collection. And in math, we usually designate sets using capital letters.
Like a capital F for flatware.
Exactly. Capital F represents the set of flatware.
Okay, but if I think about the way people actually organize things in reality, it gets pretty messy. Like, I have a junk drawer in my house.
Everyone does.
Right, and I could define that drawer as my set of useful things. But, the half-depleted batteries and random rubber bands in there, somebody else might look at that and say it's a set of garbage.
Totally.
So in math, how do algorithms or logical proofs handle that kind of subjectivity?
Well, the short answer is they don't.
They don't.
No, and this actually points to a critical threshold in mathematics. A loose category, like your drawer of useful things, that does not qualify as a mathematical set.
Because it relies on interpretation.
Precisely. For mathematics to function, we require what's called a well-defined set.
Meaning the rules of entry are absolute, like no gray area.
Zero gray area. A well-defined set clearly and unambiguously communicates whether an element is a member of the set or not. The criteria just cannot fluctuate based on personal opinion or perspective. The textbook actually highlights this contrast really brilliantly. So consider this question. What are your top 10 songs of 2021?
Oh, man. Well, that list changes depending on who you ask, obviously. Or even what mood I'm in today versus tomorrow.
Right. It is entirely subjective, which means the set of your top 10 songs of 2021 is not well defined. But contrast that with a different parameter. Say, the set of the letters in your legal name.
Ah, okay. That is an objective fact. You can literally look at a birth certificate and verify it. It doesn't matter who is observing the set, right? The elements remain identical.
Exactly. The rules are fixed. Though Section 1.1 does include this really fascinating anecdote that shows how even objective parameters can be manipulated if you understand the system.
Oh, wait, is this the football player?
Yes. The former NFL wide receiver, Chad Johnson.
The Ochocinco story.
Yeah.
He legally changed his last name to Ochocinco to match his jersey number, which was 85.
He did. And in doing so, he legally altered the elements in the well-defined set of the letters in his name.
Wow, okay. So the parameters of a well-defined set can change, but the point is that at any given snapshot in time, the criteria for membership are indisputable.
Yes, exactly. If we pull the legal records for that specific date, the set is absolute.
That makes sense. That is the essence of being well-defined. But, this strict criteria kind of opens up a philosophical paradox, doesn't it?
How so?
Well, if the rules of a set are so ironclad, what happens when a rule filters out literally everything in the universe? Does the set still exist if it has no elements in it at all?
Ah, that is a great question. Like a kitchen drawer that is completely empty.
Right. It's still a drawer.
Exactly. In set theory, this is known as the empty set or sometimes the null set.
Okay.
It's symbolized by a pair of empty curly braces
Mm-hmm.
or by a zero with a diagonal slash through it. And it is a completely valid mathematical entity. The textbook uses a highly specific historical example to illustrate this.
What is it?
Think of the set of all women vice presidents of the United States of America prior to January 20, 2021.
Okay, well, Kamala Harris was sworn in on that exact date.
Right.
So if the parameters of the set strictly specify prior to January 20, 2021, the number of people who meet that criteria is precisely 0.
Yep. The set is empty, but the set itself still exists conceptually as a well-defined categorization.
I have to pause you here because this feels like a cognitive trap.
Uh-oh.
If the empty set contains 0 items, isn't an empty set just a set with the number 0 inside it?
Oh, I'm so glad you asked that.
Eh?
It is a super common misconception, and Section 1.1 actually includes a specific checkpoint just to dismantle it.
Really? Okay, dismantle away.
An empty set and a set containing the number 0 are two profoundly different things. So think of the set as a physical box, okay?
Okay, I'm picturing a box.
The empty set is a box with absolutely nothing inside it.
Total void.
Right. Now, take a piece of paper, write the number 0 on it, and place it in the box.
Okay.
The box is no longer empty. It contains one distinct element,
Mm-hmm.
the concept of 0. So the empty set has no elements, but the set containing 0 has exactly one element.
Oh, wow. That distinction really illuminates how heavy the concept of 0 actually is. I mean, it isn't just a synonym for nothing. 0 is a tangible mathematical object.
It is. And the textbook takes a quick detour here in its Who Knew segment to explore the historical weight of 0, because it fundamentally changed human capability.
Because before that, we just couldn't do certain math.
For centuries, mathematics was literally paralyzed without it. The historical record suggests the Babylonians used early versions of 0 around 300 BC, mostly as a placeholder,
Okay.
and the Mayans developed it completely independently around 350 AD.
But using it as a placeholder, like, just distinguishing a 10 from 100, that's different than treating it as a number you can actually manipulate, right?
Exactly. The real breakthrough came from the Indian mathematician Brahmagupta around 650 AD.
Brahmagupta.
Yeah. He didn't just use 0 to hold a space, he formalized its use in arithmetic operations. He basically established the rules for adding, subtracting, and multiplying with 0.
It is so wild to think that the number 0 had to be, invented. It serves as this ultimate neutral anchor for our whole number line. And the textbook points out a really strange piece of trivia, too, right?
Oh, about it being even.
Yeah. 0 is an even number, but it is the absolute only number in existence that is neither positive nor negative.
It sits perfectly on the fulcrum of mathematics, and once humanity grasped 0 and the empty set, our ability to categorize the universe just exploded.
I bet.
But, that scale introduces a brand new problem. If we have sets that can contain millions, billions, or even infinite elements, we need a standardized language to document them.
We need rules of notation, because if you're trying to write out massive sets, the traditional method, what the textbook calls the roster method, that breaks down pretty quickly.
Yeah, the roster method is the most basic approach. You just list the elements, separate them with commas, and enclose them in curly braces.
So if your set is the primary colors, you write an open curly brace, then red, comma, yellow, comma, blue, close brace.
Exactly. It is simple and effective for small, finite sets.
But if I want to define a set of every single car currently existing in the physical world, the roster method is completely impossible.
Right, you'd be writing forever.
Yeah, I can't write out a billion cars. And a database algorithm can't process a list like that efficiently either. There has to be shorthand.
There is, and it's called set builder notation. It functions very much like the logical syntax used in computer programming.
Okay.
Instead of listing elements one by one, set builder notation provides a verbal or symbolic formula that defines the conditions for entry into the set.
It acts like a bouncer at the door of the set.
Precisely, a mathematical bouncer. So you might write a capital C for the set of cars.
Right.
Then an equal sign, an open curly brace, an X, a vertical line, and the phrase X is a type of car.
Wait, that vertical line is the critical piece there, right? How is that actually read mathematically?
It translates to the phrase such that.
Such that.
Right, so the entire notation reads, set C is the set of all elements X such that X is a type of car.
Oh, I see.
It establishes a logical test. You hold up an object to the rule. Is this object a car? If yes, it's an element of set C. If it's a bicycle, it fails this such that condition, and the bouncer excludes it.
That is brilliant. That allows you to define massive, even infinite concepts with just a single line of logic. But what if a set is massive yet highly predictable?
Like what?
Like the alphabet or counting numbers.
Ah, okay. For large sets with a natural repeating order, we use 3 dots in a row.
3 dots.
Yeah, the mathematical term for it is an ellipsis. So if you're using the roster method for the English alphabet, you don't actually list all 26 letters.
That'd be tedious.
Very. You write A, B, C, comma, then those 3 dots, comma, V. You establish the pattern, use the 3 dots to bridge the gap, and cap it with the final element.
But those 3 dots, they're also the bridge to infinity, aren't they?
They can be, yeah.
Because if you look at the set of natural numbers, the positive counting numbers like 1, 2, 3, there is no final element.
Right. In set theory, the natural numbers are represented by a stylized capital N. So you write the roster as 1, 2, 3, comma, 3 dots, and then you just close the curly brace.
No trailing element.
Exactly.
Yeah.
Without a trailing element, it signifies that the pattern just continues forever.
Which brings us to a frankly terrifying question for any student of mathematics.
Hit me.
How do you measure something that never ends? If you have sets that go on to infinity, how do you even compare their sizes?
Okay, to measure a set, we use a concept called cardinality, or cardinal value.
Cardinality.
Yep. It simply means the number of distinct elements contained within the set. The notation is a lowercase n followed by the set's name in parentheses.
Okay, so if set A has 4 elements, the cardinality, or NA, equals 4.
You got it.
That makes perfect sense for a finite set, right? The kitchen drawer has 5 utensils, its cardinality is 5. But for the set of natural numbers, which literally never stops, what is the cardinality of infinity?
Well, section 1.1 introduces the symbol used for the smallest infinite set, which is the natural numbers.
Wait, smallest?
Yeah, we'll get to that. But the cardinality of the natural numbers is denoted by a Hebrew letter paired with a subscript 0. It's pronounced Aleph Null.
Aleph Null. That just sounds cool.
It really does. It represents a countably infinite set. You can't reach the end of it, sure, but you can count it in a sequence.
Yeah.
1, 2, 3, onward forever.
Yes. So any set that has the same cardinality as the natural numbers is considered countably infinite.
Exactly.
There is a quote in the textbook about this that is just profound. It's from the mathematician we discussed at the very beginning of the show, Georg Cantor.
Ah, yeah.
He said, "A set is a many that allows itself to be thought of as a one."
That is so good.
It completely shifts how you view infinity. It takes this sprawling, terrifying void of endless numbers and packages it into a single conceptual entity. You can hold infinity in your hand as a single idea called Aleph Null.
It is a brilliant distillation,
Mm-hmm.
and it really highlights why Cantor is considered the father of modern set theory.
Oh, for sure.
The textbook actually has this people in mathematics feature that delves into his background.
Yeah, born in Russia in 1845, right?
Yes, and he was an incredibly gifted violinist, too. Plus, he earned his doctoral degree in mathematics at just 22 years old.
Which is insane. But his genius came with a massive psychological and professional cost, didn't it? Because he didn't just stop at Aleph Null.
He really didn't. Cantor proved that there are different sizes of infinity.
Which still melts my brain.
Right. He showed that the set of real numbers, which includes all the infinite, non-repeating decimals between whole numbers, is uncountably infinite.
Meaning you can't even put them in a sequence.
Exactly. You can't map them sequentially like you can with 1, 2, and 3, because between any 2 decimals, there are an infinite number of other decimals. So the cardinality of real numbers is fundamentally larger than Aleph Null.
He essentially proved that the infinite universe has layers.
Yes.
And the mathematical establishment absolutely hated him for it.
They despise the idea. The text notes that Cantor faced aggressive, massive objections from prominent figures, most notably his former professor, Leopold Kronecker.
Ouch.
Yeah, at the time, infinity was viewed almost as this divine absolute. To claim there were multiple infinities and to try and categorize them was seen as mathematically absurd and philosophically dangerous.
It is the classic story of the visionary being punished by the establishment. I mean, Cantor was just trying to solve what became known as the continuum problem, trying to figure out if there was another size of infinity sitting between the countable integers and the uncountable real numbers.
The struggle took a severe toll on him mentally. But his brilliance could not be suppressed forever. His framework proved so essential to modern logic that he was ultimately awarded the Sylvester Medal from the Royal Society of London in 1904.
Talk about vindication.
Totally. He built the foundation that allows us to manage infinite data today.
So thanks to Cantor, we have finite sets, countably infinite sets, and unaccountably infinite sets. With all these different categories, I think the final piece of the puzzle is how we actually relate them to one another. Like, if I'm looking at two different sets, how do I accurately compare them?
Okay, we use two very specific terms that people actually mix up in everyday language all the time.
Which are?
Equivalent and equal.
Okay.
In mathematics, they mean entirely different things.
Let's define the boundary between them then.
Okay. Equivalent
Mhm.
means two sets have the exact same cardinality. They contain the same number of elements.
Right.
Equal, on the other hand, means the two sets contain the exact same specific elements. Order doesn't matter, but the contents must be identical.
Okay, let me try an analogy to test this, because visualizing physical objects usually breaks down around here.
Let's hear it.
If I go to a car dealership and I see two Honda CR-Vs sitting next to each other, painted the exact same color, built on the exact same assembly line, are the sets containing those cars equal?
No. And this is where we have to be incredibly precise.
Okay, why not?
If you create a set containing physical car A and a set containing physical car B, those sets are equivalent because they both have a cardinality of 1,
Right.
but they are not equal sets.
Ah, because physical car A has a different VIN number, different atoms, and occupies a different space than physical car B. They are distinct elements.
Exactly. For sets to be equal, the elements must be fundamentally the same entity.
Got it.
If set X contains the 16th President of the United States and set Y contains Abraham Lincoln, set X and set Y are equal, they are just two different ways of defining the exact same element.
That clarifies it perfectly.
Yeah.
Equality demands identical elements. Equivalence just demands the same head count.
You nailed it. And the textbook scales this up to a dealership inventory to demonstrate equivalence.
Oh, sticking with the cars, I like it.
Yeah, imagine the lot has 10 RAV4s, 8 Priuses, 7 Highlanders, and 12 Camrys.
Okay, so we have 4 types of vehicle models.
Right, so if we create a set of the vehicle types, the set is RAV4, Prius, Highlander, Camry. The cardinality is 4. Now, create a separate set of the quantities in inventory, 10, 8, 7, and 12. The cardinality of that set is also 4.
Oh, I see. The elements are completely different. One set is made of abstract car models, the other is made of integers, but because they both contain exactly 4 elements, they are equivalent sets.
Exactly. They can be mapped to one another in a one-to-one relationship. Symbolically, we represent equivalent sets with a tilde, small wavy line between the letters.
So A tilde B?
Yep. Equal sets just use the standard equal sign. And Section 1.1 provides a really critical checkpoint rule to tie these two concepts together.
And the rule is, if 2 sets are equal, they are always equivalent.
It is an unavoidable logical truth. If 2 sets contain the exact same elements, they must inherently have the same number of elements.
But the inverse is entirely false.
Right.
Just because 2 sets are equivalent, like the car models and the inventory numbers, does not mean they are equal.
Yeah. Exactly. It's a structural hierarchy that allows databases, search engines, and algorithms to relate different types of data without confusing their actual identities. You're comparing cardinalities to find equivalence while preserving the uniqueness of the elements themselves.
Which really brings this entire deep dive full circle, honestly.
How so?
Well, as a student today, stepping back from the notation and the Greek letters, you realize this isn't just theory. We started with the messy kitchen drawer and realized we need well-defined rules to organize anything.
We did. We saw how the invention of zero and the empty set gave us the ability to quantify absence, which completely opened the door to advanced mathematics.
We looked at set builder notation, which is the exact same such that logic that runs the search algorithms we use every single day.
Yep.
And we peered over the edge of infinity with Georg Cantor and learned how to wrangle the endless into Aleph null.
And we learned to untangle our comparisons, right? Separating sets that are merely equivalent in size from those that are fundamentally equal in substance.
It's just amazing. Every time you navigate a digital folder system, every time a streaming service recommends a movie based on a set of your past preferences, and even every time you weigh equivalent options to make a decision in your own life, you are operating within the boundaries of set theory. You are applying section 1.1 to reality.
The mathematics simply gives us the language to describe the categorization our brains are already desperately trying to do.
So as we close the book on this deep dive, I want to leave you with a final thought to chew on.
Lay it on us.
We have established that every single object, concept, and piece of data in our physical world can be categorized, filtered by such that logic, and grouped into a mathematical set.
Right.
So taking Cantor's logic to its absolute furthest extreme, is the entire physical universe itself just one massive, uncountably infinite, well-defined set?
Wow. A single set containing the totality of existence.
Yes. And if the universe is just one well-defined set, what exactly lies in the empty set outside of it?